Hello everyone, this is Maram Alkhlaifat, a doctoral candidate at TUM within GECKO, and this is my pitch. GECKO is a Marie Curie project in the field of isogeometric analysis, and within we're 10 different doctoral candidates focusing on different areas. And mine comes in developing a robust structural elements within a large deformation context and incorporating these approaches in an open source software called 𝗚𝗘𝗢𝗨𝗧 𝗚𝗘𝗢𝗍. Now, why does this matter? Because in traditional finite element method, it did show some disadvantages within geometric accuracy. And what isogeometric analysis and what IBRA does, the isogeometric boundary representation analysis, that it does use the same CAD model for design and analysis, ensuring that we have an exact geometry. This becomes quite handy within industrial applications. And the more realistic your results, your simulations are, the better prediction for real world behavior. And this will help to make the prediction and the decision of the improving your design and choosing better materials. Now, in my PhD, I started with the shell element. And why is that? Since in the shell element we have the mud surface assumption, which serves as the dimension reduction feature, because instead of dealing with a 3D model, now we're using a 2D model. And it's a better example to show the bending and membrane behaviors. So which kind of shell did we start with though? We have two famous ones, the Kirchhoff-Love and the Rasen-Medlin, and the choice was to go with the Rasen-Medlin shell since it deals with both like thick and shell and thick and thin, and also it deals with the transverse shear deformation. Now there's already some formulations within the open source software 𝗚𝗘𝗢𝗨𝗧. And the idea was, why not to introduce another Rasen-Medlin shell that is that has like low computational cost and expand the family. And if we go now to the theory, like to the literature, it started with that shell in isogeometric analysis with Kirchhoff-Love ones, and with the work of Kendall in 2009. And there we managed to see that there's like the strains can be clearly defined into like membrane part and a bending part. And then within the Rasen-Medlin shell, in work of Benson in 2010, we see that the same concept goes to the B matrix, which the matrix that can exert displacements with the nodes, like with the locations. And then there's a recent paper last year with the work of Do that explains more in details about this procedure. And now I mentioned these main three papers because they served as a baseline for my shell formulation. And then it needed a little tweaking to be in the 𝗚𝗘𝗢𝗨𝗧 environment, a framework. So let's test it out, starting with a cantilever plate under a vertical world, which is simple example. And we can see on we are using the 𝗚𝗘𝗢𝗨𝗧 multiphysics for the formulation, and then visualizing it in Rhino. And we can see that on the left we have the using like Kirchhoff-Love shell elements, and on the right the Rasen-Medlin, and we are getting very approximated results. Okay, I might have misused the word. I mean, we have very, very similar results, not approximated, because we have an exact geometry. Okay. Now, Cordelia's roof. The thing here is that we have a curved shell now, and so our normals, they need some editing, because now we need to, because they do change with the deformation, so we need to have the derivations of the normals integrated. And now the comparison was actually being done with the Kirchhoff-Love and the work of Kendall. So we can see on the left that we have the same Cordelia's roof, same geometries, and then the playground is that refinement. So whether P refinement, the polynomial degree, increasing it, and also inserting more knots. And the base is 0.3, and we can see that we're obtaining very similar behavior. And the only thing that is here is a bit unpleasant. It was like a little bit of fluctuation when the polynomial equals to 4, which at this point needs further testing to be certain to say what was the reason. But all in all, okay, good. So we continue to a pinch cylinder, and in this case, we see that we're obtaining very similar behavior as well with the Michel element formulation and the 𝗔𝗕𝗢𝗨𝗧. And the thing though is, we can see that here my reference value is 1.8 to the power of minus 5. We can see that we're already converging at almost 15 control points per side. Let's say 20, okay? In the Riemann case, we do see that we need more refinement, and we get to the same thing, when almost 60 control points per side, which is getting too much. If we do look at the same range, so what would happen when we're at our shell in the Riemann and we're like at 40 control points, we see that there's a little bit in decrease, and we are obtaining values around 1.6. So the thing here is we might be suffering from locking because we do have shear deformation in the formulation. So this requires some treatment, which is a part of my upcoming areas that, or let's say upcoming directions. And other direction include the nonlinear behavior, so whether it's coming from material or geometry, and then the trimming and the coupling issues, and we'll see how that goes. And this leads me to the end of my presentation, and thank you so much for watching.